Hello, welcome to Lecture 7. In this lecture, we're going to talk about interference of waves with examples about sound waves in 2 dimensions and 3 dimensions. So far, we've only talked about one-dimensional interference, but of course, interference also happens in 2 dimensions and 3 dimensions, and we can see that all the time. Let's look at a short video about interference in water waves.
Where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference and there's basically no wave there. And this is exactly what was happening with the light.
Okay, so in our video, the speaker goes on to talk about light interference, and that certainly happens, but we'll just cut off the video there. So we definitely know that interference happens in 2 dimensions and 3 dimensions. When we talked about one-dimensional waves, we had that the height of the wave y depended on horizontal position x and time t. Now for 2-dimensional waves, we call those circular waves. In 3 dimensions, we call them spherical waves. And in both cases now, the height of the wave y depends on the position, but we use d for distance from the center, okay? Otherwise, the equation is the same, and the interference treatment is the same. Where the waves meet up crest to crest, those are the blue lines in the diagram, we'll get constructive interference, and where they meet up crest to trough, and a trough is between two crests, where they meet crest to trough, we'll get destructive interference. The video we just watched shows interference in water waves, but we said that we can have interference with sound waves. Is that a real thing? Can you really observe it? I went and I recorded a demo to show you. I'm in a classroom on campus. It's pretty empty here. All the chairs are up on the desks and stuff. What I'm going to do for you is a little sound experiment that I would normally do in class. In this classroom, there's speakers up on the walls. So there's one there. There's one over on this side. What I'm going to do is I'm going to play a single frequency tone on the desktop computer here. I've got it set at 343 Hertz. It's a little bit loud, and I'm going to hit play. Okay, I hope you can hear that. Now I'm just going to walk around a little bit. So listen as I move. Okay, hopefully you can hear what I hear, which is that the sound alternately goes loud and quiet as I move around. That's interference in the sound waves. The loud spots are where it's constructive interference, and the quiet spots is where it's destructive interference. Okay, let's do an example that's similar to what we did with the one-dimensional interference. So we have two sources of waves. One of them is represented by the green circles. So these are the crests of the green wave of one source. And then the other wave is represented by the blue circles. Those are the crests of what we can call the blue wave. So we have two waves. We know that there are troughs between every crest. So this is a blue crest, a blue crest. There's a trough in between the crests. Here's a green crest, here's a green crest, there's a trough in between the crest. The question asks, what kind of interference happens at the position of the black dot? So let's first answer that question by asking, does it meet crest to crest, trough to trough, or crest to trough? Because crest to crest is constructive, trough to trough is constructive, and crest to trough is destructive. So for our black dot, for the green wave, it's between two green crests, so it's at a green trough. Let's look at our blue wave. For our blue wave, that black dot is between two blue crests. That means it's at a blue trough. So our wave meets up trough to trough, which makes it constructive interference. And if these were speakers, we'd be hearing loud sound. Okay, let's put a little math to it. What if we wanted to think about the path difference? So I'm going to call my top speaker, speaker 1, and the distance between my dot and speaker 1 is D1. I'll label that one green because my top dot, this is my source number 1, and the green circles or the green wave is coming out of this one. My lower dot, my lower source, I'll call that source 2, and my distance between my second source and my dot is distance D2. Let's write D1 and D2 in terms of the wavelength. Now, let's remember wavelength is the distance between any two crests. So there's a wavelength on my green crest. So let's see how far away is my black dot from my source. So I go source to crest, that's a full wavelength. Then I go crest to trough, that's a half a wavelength. So D1 equals 1.5 wavelengths. What about D2? So D2, or my wave 2, from crest to crest is a wavelength lambda. The wavelength from my blue wave is the same as the wavelength for my green wave. And let's see how far apart are my source and my dot. So from the source to the first crest is lambda, to the second crest is 2 lambda, to a trough is 2.5 lambda. D2 equals 2.5 lambda. Now I'll find my path length difference, delta D, which is D2 minus D1, take the absolute value because it doesn't matter which is bigger, is 2.5 lambda minus 1.5 lambda, gives us 1 lambda, and that was constructive. So we can follow the same process as we did with one-dimensional interference, and we'll get the same equations for constructive and destructive interference. So our conditions for interference in 2 and 3 dimensions is the same as for in 1 dimension. If we have two sources emitting waves or sound in phase, that means that the two waves come from the two sources in the same way, for example, both on a crest, then we'll get constructive interference if the path difference is equal to an integer multiple of the wavelength. And we'll get destructive interference if the path difference is a half multiple of the wavelength. If our two sources are out of phase, so for example, one source emits sound on a crest and the other emits on a trough, then our conditions flip. We'll get constructive interference if the path difference is a half integer multiple of the wavelength, and we'll get destructive interference if the path difference is an integer multiple of the wavelength. Here's a homework example for you to try. I won't make a video, but I will post the solution if you want to see it.